Ask a modern language model an isolated reasoning question, and you will typically get a flawless, coherent answer. But drop that exact same model into a live environment and tell it to operate autonomously, and the logic often fragments into chaotic, looping errors. We are watching a clear paradox in the industry right now. Foundation models are scaling up in parameter count and raw reasoning capability, yet their reliability when executing long-horizon tasks in production remains highly brittle. Generating a response to a single, stateless API call is a contained math problem. Managing a stateful, continuous execution loop across changing environments requires durable memory, error recovery, and strict operational boundaries. When an agent deletes a necessary file or gets stuck repeating the same failed API request, the model's neural network isn't broken. The infrastructure governing its environment has failed. For real-world tasks, the underlying foundation model is no longer the primary bottleneck. The success of an autonomous agent is dictated by the engineered system wrapping the model, rather than the model alone. This surrounding infrastructure is called the agent harness. It is the software bridge connecting a raw language model to live execution. A raw model can only output text. The harness takes that text, parses it, applies permissions, invokes physical tools, and writes state to memory. It turns theoretical instructions into bounded, observable actions. This diagram illustrates the evolution of how engineers control model behavior, moving left to right. The pipeline begins with single-call prompt engineering, expands into multi-step context engineering, and finally arrives at system-level harness engineering, which governs how the model runs. Each phase in this sequence didn't replace the last. It evolved to solve a specific execution failure that the previous phase lacked the mechanical ability to address. Mastering this complete evolution is a strict requirement for taking AI agents out of experimental local scripts and embedding them into robust enterprise systems. The earliest and most basic form of control targets the input. Prompt engineering optimizes a static text string before it is sent to the model. Look at this baseline system prompt. It assigns a rigid persona, a medical billing specialist, and maps out explicit constraints, demanding codes from a provided table. The rules also force a JSON output format. Enforcing this upfront prevents downstream parsing errors. Here is a technique called few-shot prompting, which includes labeled examples of the desired output. Zero-shot instructions often fail when category boundaries are ambiguous. By explicitly providing edge case examples directly in the input, the engineer anchors the model's statistical weighting, reducing classification errors. Engineers also inject chain-of-thought instructions, forcing the model to render its sequential reasoning steps into the context window before committing to a final answer. But relying purely on the prompt creates an immediate failure mode. It is a completely stateless, single-turn optimization. Once the model outputs its response, it retains no memory and cannot adapt to what happens next. Prompt engineering perfectly constrains a single turn. It is entirely insufficient for guiding an agent through a 30-step autonomous workflow. When an agent operates continuously, the engineering problem shifts from formatting instructions to curating the flow of information over time. Every model has a finite attention budget. If you eagerly load an agent's context window with entire codebases and thousands of previous messages, the critical instructions get diluted, and performance degrades rapidly as relevant data spills out. The solution is progressive disclosure. Instead of dumping everything up front, the system dynamically retrieves and filters data, allowing only the most immediately relevant information through the bottleneck at any given step. This requires building a multi-tiered memory hierarchy. Engineers must manage the active context window for immediate processing, a session-level state for the current task, and a long-term vector database for historical retrieval. Without careful management, an agent suffers from context rot. Stale error messages or outdated tool results accumulate, confusing the model. The system must actively prune old state data to keep the attention budget clean. Managing memory solves the information flow. But a well-informed agent with perfect context still cannot physically execute code or catch a systemic API failure. The static model becomes a dynamic actor at the single-agent inner loop. This is the continuous cycle where the model begins interacting with external environments. It operates on the react paradigm. The model observes the current state of its environment, reasons about the gap between that state and its goal, and decides on a specific action to take next. Deciding to take an action is useless unless the harness translates that decision into physical execution. It does this by exposing specific external tools to the model. For an agent to use a tool, the developer must provide a strict open API schema. In traditional software, a schema is documentation for a human. For an agent, it is a rigid runtime contract dictating exactly how to format the data packet. If that schema lags behind the live production API, it actively trains the agent to fail. The agent will confidently output tool calls that the server immediately rejects. The harness must catch those server rejections, or any successful output, and route that environmental feedback cleanly back into the start of the agent's next observation cycle. Orchestration creates autonomy. But unleashing a looping, self-prompting system with live API access into a production environment carries immense security and cost risks. This requires a very hard architectural boundary. This diagram shows the ETCL-OVG framework, a 7-layer architecture providing the mandatory oversight required to safely deploy an agent. It begins at the execution layer. Generated code cannot run directly on your main server. It requires sandboxed runtimes to limit blast radius. The tooling and context layers maintain API capabilities and memory states. The lifecycle layer provides orchestration, acting as the conductor that coordinates reads and writes between sandboxes, tools, and memory. Moving outward, the observability layer tracks system-wide telemetry, allowing administrators to kill an agent burning cache in infinite loops. The verification layer captures full trace histories to run offline evaluations and build regression tests. Finally, the governance layer wraps the entire system. It enforces identity controls, struct tool permissions, and human-in-the-loop approval gates before any high-risk action is executed. Implementing these 7 specific layers is the mechanical difference between running a fragile experimental script and maintaining a resilient enterprise system. This heavy infrastructure creates a new architectural problem. What do you do with a complex harness when the underlying foundation model gets significantly smarter overnight? The answer is the harness as assumption principle. Every harness component exists exclusively to mitigate a deficit in the model's capability. If it lacks attention, you build memory pruners. If it can't plan, you build evaluator loops. The harness is a cast around a broken bone. Anthropic recently demonstrated this when they upgraded a production coding agent from their Opus 4.5 model to the newer Opus 4.6. They found that previously mandatory constraints, like forced context resets and rigid sprint evaluation structures, were actively holding the new model back. They removed them entirely, and the system maintained its output quality, while dropping operating costs from $200 down to $125. If your harness does not evolve alongside the capabilities of the foundation model, it stops being a safety net. It becomes bloated technical debt. The long-term goal of advanced agent engineering is adaptive simplification. This means building a system that evaluates its own necessity, shedding the scaffolding the moment the core model is strong enough to stand alone. Engineering teams must continuously monitor their production traces to measure which harness interventions are actively preventing errors and which have decayed into legacy artifacts. By running shadow mode A/B tests across different variations of the harness, developers can optimize the system for quality, latency, and cost simultaneously, rather than guessing what the model needs. The scale of a neural network determines its potential, but right now, the quality of the infrastructure surrounding it sets the absolute ceiling on its real-world reliability. While researchers race to add billions of parameters to new models, the day-to-day reality for practitioners is the granular, unglamorous work of building execution controls. To deploy functional autonomous systems today, engineers must construct rigorous architectures to keep them safe. But the best engineering teams are already designing the mechanisms to systematically strip that scaffolding away tomorrow.